All right, so as we wrap up Chapter 6, Section 6.3, we're going to talk about geometric distributions. We went through the binomial distributions and the settings yesterday. A geometric distribution is in a binomial setting is the number of trials and in a fixed, as we learned about that. It's a repeated chance situation until the first success occurs. So there's the difference there. So when we look at what's the difference between a binomial and a geometric, in a binomial random variable, we're just trying to figure out in a some chance process what's the probability of 5 successes in 10 attempts, or 6 successes in 10 attempts, or greater than 4 successes in 10 attempts. Well, in a geometric, we actually keep repeating the process until we finally get a success. So there's actually a whole bunch of failures, and we're trying to find the probability of when I'll get my first success at this thing or this trial. And there's no end. So there's no fixed number of trials in a geometric setting. It's open-ended, is what it basically is. So it'd be and we have some, may have some examples like this, but if we think about basketball, because it's that time of year, March Madness getting ready to happen in a month, and we always look at people, girls and guys, hitting the free throw line, and they say, hey, they're a 70% free throw shooter, or they're a 85% free throw shooter. And we can do a binomial setting where we're saying, okay, if this person averages 6 free throws a game, and they're an 85% free throw shooter, what's the probability they make 5 out of the 6 shots? And that would have been a binomial distribution that we did in the previous lesson. Now, we would turn it for a geometric setting. We would say, all right, yes, you're an 85% free throw shooter, but what's the probability you don't make your first free throw until the 5th free throw? So you had 4 misses, and then all of a sudden you make one. So we're trying to figure out, well, what's the probability of that happening? What's the probability of me making it on the 2nd free throw is my first one. So that's the difference with the geometric is we don't have a fixed number of trials. It's just, hey, when is my first success going to happen? And so it's a whole bunch of failures, and then finally one success is what we're trying to figure out. So there are 4 conditions for checking for the geometric. We changed our acronym from bins to bits. The binary is still the same. Is it basically success or failure? Those are the 2 possible outcomes. Independent. One trial is independent from the other, knowing that whatever happened has no effect on the next one. Now here's the difference. Instead of having a fixed number of trials, it's open-ended. It's open until basically we're going until I get the first success, is what's happened. Now we do see the CDF versions, the cumulative frequencies on this one, taking place or probabilities. And again, our successes, it's still got to be the same each time. So our probability of success stays the same every single instance. The number of trials Y that it takes a person to get successes in a geometric random variable. How do we figure it out by hand? Here is what the probability model is based off of. The probability that I get my success on whatever the kth trial is, we basically do 1 minus the probability of success raised to the k minus 1 power times the probability of success. The probability of success, always, this one right here, always has a power of 1 on it. All right, it's just one success because we're going to be actually looking at, I have a bunch of failures, and then finally my first success. So whereas the binomial, it kind of altered the exponents based on which trial you were doing, as you were doing things. Like the binomial random variable, it's important to be able to distinguish situations in which the geometric distribution does and does not apply. So that's where we got to make sure that we go through the bits. If we meet the criteria for bits, then we can do a geometric situation. Okay? All right, first one here, it says a student will be selected at random from a class and asked to guess the day of the week on which one of the teacher's friends was born. If the student guesses correctly, then the class will have only one homework problem. If the student guesses incorrectly, the teacher will again select a student from random from the class. The student will try to guess what day of the week a different friend was born on. And if they get it correct, the class only has to do 2 problems. So in this case, the random variable of interest in this game, y, is the number of guesses it takes to correctly identify the birthday of one of your teacher's friends. What is the probability that the first student guesses correctly, the second student, the third student, and the kth student? So as we go through checking our conditions for the BITS acronym, success is when they guess correct. Failure, they didn't get it correct. Independent, the results of one student guess has no effect on the results of any other guesses. Because remember, it said in that situation, a different friend. Okay? If it was the same friend, well, if I already know you chose Wednesday, am I going to choose Wednesday? No, so that changed the probability. Because if it was the same friend over and over again, we went from 1 out of 7 to 1 out of 6 to 1 out of 5. The probability of success changes if we stay with the one friend. So that's why it talked about in this situation, a different friend. That way it's still a 1 out of 7 successful probability each time. Okay? T, we're counting the number of guesses until we get the first correct guess. And then each trial, the number of correct guesses is 1/7. And that's what by the changing friends, that's what that did. So what they did for us, they calculated the three different situations. What's the probability they get it correct on the first example, the first try? That would be 1/7. And because that's the probability of success. In the formula, we would have had 6 out of 7, because that's 1 minus p, to the 0 power, because basically that was 1 minus 1. And then we times 1/7. And so 6/7 to the 0 power is just 1. And then 1/7 times 1 is just 1/7. So that's why that worked out to be 1/7. Now that we said, okay, what is the probability that it happened on the second guess? So we have on our formula here, it is 6/7 raised to the 2 minus 1 power times 1/7. So that's how it would work out in the formula, is what that would work out. So that's why we just see 6/7 times 1/7, because 2 minus 1 is to the first power, so it's listed once. On the P for the third guess, again, formula-wise, we would look at 6/7 to the 3 minus 1 times 1/7. So that's 6/7 squared times 1/7, and then that's why we see the 6/7 times the 6/7. Okay, so do we notice a pattern? Well, yeah, for each number of guesses it takes, what am I putting onto the previous formula? Another 6/7. We're just adding an additional 6/7 to the previous formula. As my number of trials increases till I get a correct guess, then I'm just adding another 6/7. Another failure percentage is being combined to what was there before, what was being multiplied to what was there before. So that's the pattern that we notice, is that as y increases, until the first success occurs, an additional failure percentage is combined with the previous answer in order to get to our answer there. So I'm not going to write anything down. That was just kind of get us to talk about it. So in this next part here, it says if y has a geometric distribution with probability of p of success on each trial, the probability values of y are basically 1, 2, 3, so forth. So they're whole numbers. We wouldn't worry about 0 in this case. In the binomial setting, it made sense, to have the 0 there, because what's the probability of, in 10 free throws, can I miss all 10? Sure. So there's a probability of that happening. So with our there we go. There's my notes. I'm trying to figure out where my notes were. So again, our formula, real briefly here, is 1 minus p to the k times whatever p is. So in the board game Monopoly, one way to get out of jail is to roll doubles. Find the probability it takes 3 turns to roll doubles. So what's the probability that y is equal to 3? Now you can use x if you want to. They just happen to this thing define y as our thing there. So that would mean I would do, we know, what is the probability to roll doubles? We know it's one, like a 1 and a 1, a 2 and a 2, and a 3 and a 3, and a 4 and a 4, and a 5 and a 5, and a 6 and a 6. So that's 6 successes out of 36 total opportunities. So it's just 1 out of 6. So the probability of success of rolling doubles is 1/6. So as we look at formula, this would be 5 out of 6 raised to the 3 minus 1 power times 1 out of 6. Again, the first fraction is always 1 minus the probability of success. So 6/6 minus 1/6 is 5/6. So then this turns out to be 5 to the 6th power squared times 1/6. And that's really just 25 out of 216. And if we get a decimal version of that, it's going to come out to be about 0.1157. Now, we learned about using the calculator to help us with binomial distributions yesterday. We can do the same with geometric distributions. So if I go over here, pull up my handy dandy calculator. If you're using mine, my college stats kids were doing some crazy junk in there with the tables and stuff, so you might want to clear it. So I'm going to do a second plus 712. And now we're going to go second vars. It is on the back menu, and it's actually down at the bottom of the back menu, so I'm going to arrow up. And again, we said exactly, probability that y is exactly 3, which means I need to use a geometric PDF. I usually abbreviate it just GeoPDF is what I usually abbreviate it as. And so when I choose geometric PDF, notice I don't have as many things I have to type in. We have to type in the P, which will be 1/6. And then now we type in, when are we having our first success? This is where y is equal to 3. So I'm going to type in, I'm going to do alpha y equals to give me a fraction and type in, never mind, don't do that. Just do 1 divided by 6. So just type in the fraction, 1 divided by 6. Don't turn it into decimal. If you do turn it into decimal, you're going to have to go like 0.1666666666 to trick it into thinking it's a repeating decimal. And then my value is 3. And hit enter a couple times. And there's my 1.57. 0.1157. So there's an 11% or 11.5% chance that the first success of rolling doubles will be on the third try. That's what that's saying. It's going to take. It's going to. In order for it, it's going to take me about a 12%. It's going to take me for where the first where I get my first success is on the third try. Find the probability that it takes more than 3 and interpret this. So they want us to write a sentence about this one. So again, this one, probability that y is greater than, more than 3. More than 3 is actually technically greater than 3, is what that is. So it's not even an equal to. Okay? More than 3 means 3 is not included in what the answer we want. So this is where we would do anything with greater than, we got to do the 1 minus. So 1 minus the probability that y is less than or equal to 3. So because again, just like the binomial distribution, the geometric one only does to the left. It does less than. So if we're doing anything that indicates greater than, then I need to do the 1 minus. Now, again, since I said more than 3 turns, then that means I want it to add up 1 turn, 2 turns, and 3 turns, get those decimal percentages and subtract it from 1. So that's why I made my statement to say I want it to be less than or equal to 3. If we just put down, if we interpret that, if we didn't include the 3, most of us would probably just put 2 down there, and that means we're missing that whole 3 percentage amount. So now I'm ready to go through and say 1 minus a geometric CDF, so geometric CDF. Again, 1/6 is my probability percentage, and then I'm again put y equals 3 because I want it to include the percent for 3. So 1 minus second vars. The last option there, geometric CDF. Again, 1 divided by 6. 3. Hit enter a couple times. and I find out that it is 0.5787. And then now they want me to interpret what this means. So real quickly, we can say there is a 57.87% chance that it will take more than 3 rolls to get doubles. Again, what's the percent chance of getting it on the first try? Taking 1 roll, getting doubles. Just a little sidebar. What's the probability that y was equal to 1? Remember, that would be basically 5/6 to the 0 power times 1/6, which is just 1/6. So there is a 16.6 repeating percent chance of getting that on the first roll, getting doubles. Okay? So that's a small percentage. Not super small, but it's a small percentage to get it on the first try. There's a greater percentage for it to take more than 1 to do it. We know more than 3 is 57%. Okay? So, all right, next part. What is the mean or the expected value? Remember, expected value, no matter what context we're talking about, is the mean. We want to associate those words together. What is the mean of the geometric random variable? If y is our geometric random variable with a probability of p of success on each trial, then its mean or expected value is, and here's some of our notation, e sub y is equal to mu sub y, which technically, mathematically, we just got to do 1 divided by p. All we have to do here is take 1 and divide it by the probability of success. And that will tell us what our expected value is or what our mean is of a geometric situation. Remember, with binomial, it was more involved. It was doing n times p. Here, we just got to do 1 over p. So, on the Monopoly game, one way to get out of jail, as we talked about again, is rolling doubles. If this was the only way to get out of jail, how many turns would you expect it to take on average? Well, how much will we expect? Okay, so that's my expected value. My expected value of y, which is mu sub y, is equal to 1 over 6, which is 6. So on average, I should expect it to take 6 tries, is what that's saying. On average, we would expect it to take 6 tries until you roll doubles. Now, how many of you all play Monopoly and you change some of the standard rules? Anybody play it and change it, tweak it a little bit? Have family ways of tweaking it? Yeah. So sometimes you could say, like on that one, you know what? I wanted to make it harder for people to get out of jail. So instead of saying there are 6 possible ways, you just narrow down maybe, hey, the only ways to get out, double ones. Now my probability of success is 1 out of 36. And so then now that would change. It would take us on average 36 tries to maybe roll the double ones. That's what I would expect to happen, 36 tries. Okay, so you could, if you wanted to make the game interesting, change things up a little bit. You could, and that would of course change the expected number of trials you got to go through until you would roll that double. Okay, determine whether each of the random variables described below satisfy the conditions for binomial, geometric, or neither. So all of them are accountable for it. Okay. Support your case in each case. So first off, draw a card from a standard deck of 52. Observe the card. Return it to the deck. So I'm thinking independent. Sweet. And shuffle. Count the number of times you draw a card in this manner until you observe a jack. Until you observe a jack. Until means that there's no fixed number of trials. I have a bunch of failures, and then finally I see a jack. So to me, I'm thinking geometric. Now, what supports my cases? Binary. My success. Remember, we have to explain this. I see a jack. Oops, sorry. Jack has a C in it. Jack. And then my failure. No jack. Independent. Replacement of card. Guarantees independence. Or assures independence, whatever word you want to use there. Now, here's why I'm saying it's geometric T. Repeat until first success. We keep repeating until I have the first success of a jack. And then the S, the probability stays the same each time. Probability is the same each time. 1 out of 13. Four jacks in a deck, 52 cards, so 1 out of 13. Probability of success, 1 out of 13. All right. There's my supporting information why it's geometric. B, yo.
What's the first word after the S?
Probability. I abbreviated PROB. Sorry. PROB. I got lazy. Didn't feel like spelling all the other letters. Ability doesn't have much of a, Joey buys a Virginia lottery ticket each week. X is the number of times in a year that he wins a prize. All right, so it didn't say how many weeks go by until he wins. It just said how many times he wins in a year. He buys it each week. All right, so I'm thinking binomial. So let's see if I support that. My B, binary. A success. I win. Failure. Don't win. That's better than saying lost. So, I. Well, it should be independent because whether I win one week doesn't affect whether I win the next week because picking a lottery thing has no effect on the other. So, one lottery ticket doesn't affect another. Or we could say 1 week, 1 week doesn't affect the other when I do it. N is equal to 52. There's 52 weeks in a year. Because they're asking me where it's how many times I win in a year. All right, there's a set number of weeks. All right, so there's my fixed number of trials. And S, the probability of success stays the same. Okay. So same probability each week. All right, so I suppose, next example, suppose that 20% of a herd of cow is infected with a particular disease. What is the probability that the first diseased cow is the third cow? All right, so with that in mind, this one's they say the first diseased cow is the third. So I know this has got to be geometric. So I'm going to let x equal 3. So I want to find the probability that the first diseased cow is the third cow. So that's just a geometric PDF. My probability of success is 20%, so 0.2. Oops, sorry. And then my x is equal to 3. So we're just going to grab the calculator and then do second vars. Get down to, whoops, go that way. Mr. Stevens. Second, I'll clear out of there. This is where, like, you know, I talked about like tips. This is where doing second mode to quit the screen you're on. If I just made a mistake and went into a CDF, and if I go flat out and straight go second vars and I go up to geometric PDF, it's going to put that in the probability for the CDF. And so that's why doing second mode to quit the screen gets you out of that kind of stuff. And that's why, as we've been doing stuff, I usually say, hey, press second mode to quit the screen. Like when we're in the table, when they're in those things, because some of the functions in the calculator, if you just quickly go to say, oh, I picked the wrong one, it's going to put it into one of the categories that you were just in and stuff. So that's why I was trying to tell you to kind of get in that habit. So second vars, geometric PDF. Then we say, okay, probability of success, 0.2. And third cow. And paste, enter. Okay, 0.128. So it's going to be, so it's going to take us, there's a 12.8% chance that the first diseased cow is the third cow we encounter. So there's a 12.8% chance that the first cow we come across would be that would be the third cow that has the disease. What is the probability that 4 or more cows need to be tested until a diseased cow is found? All right, so probability that x is greater than or equal to 4, because it said 4 or more, which means greater than or equal to 4. So I need to do a 1 minus the probability that x is less than or equal to 3 is what I need to do. I need to use the complement rule. So 1 minus second vars, geometric CDF, 0.2 is my probability, 3 is my x value, and we get 0.512. So there's a 51.2% chance we won't get our first diseased cow until the fourth or more cow, until we get their first diseased cow. So there's a 48.9 or 0.8% chance I find the diseased cow in the first 3, but there's a 51% chance that I won't get my first diseased cow until I get to the fourth cow or more. Okay. Almost done. Last problem here. So research suggests that about 24% of the 12-year-olds in the United States can pick out the state of Colorado on a map. We should do a contest. Can you, without looking, can you draw the United States roughly, and can you put where the states are and rough size and dimensions of the states? Can you do that? All right. I see a lot of shaking heads. No. Now, I didn't say capitals. Capitals will be even harder. But all right. So what is the probability that you must sample exactly 5? Well, exactly 5, we know that means that we use the equal to sign. So what's the probability that x is equal to 5? So Again, until we find the first one. Again, until we find the first one. So this is, again, still a geometric. So geometric PDF. Probability of success is 24%. And then x is equal to 5. And so second vars, geometric PDF, 0.24 and 5. And we get 0.0800. So there's an 8% chance that it'll be the fifth. It'll be that we would find it at the fifth student. What is the probability? What is the probability you must sample exactly 5 to find the first one? And the next one, what is the probability that you must sample 5 or more? So what's the probability that it's going to? I have to do 5 or more. Now I said 5 or more, so 1 minus the probability that x is less than or equal to 4. I want 5 in my answer, because it said 5 or more. So that means I want 5 in the answer, so I have to go down and put 4 as the x value. So 1 minus geometric CDF x, and then we got to do p is 0.24, x is equal to 4. So second var, ching ching, boom, 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 boom. Change those.